Hello everyone. In this video, we're going to be doing a review for what we've learned about limits, specifically kind of preparing for an exam on the topic. So I have 25 questions here that I want to go through to kind of practice a bunch of the stuff that we've looked at. So the first question says to determine whether the sequence is convergent or divergent. And if it's convergent, find the limit. If the quantity diverges, we just write diverges. So our first limit is an is equal to 5n plus 2 over 3n minus 1. So what we're looking at for this is we want to see, as we take the limit as n goes to infinity, what is happening with this specific sequence. So we're just going to plug in this for our sequence, and we'll have the limit as n approaches infinity, 5n plus 2 divided by 3n minus 1. And we want to determine whether this converges or diverges. So using our tricks, if we first were to just try plugging in infinity, what are we going to get? We're going to get 5 times infinity, which is infinity, plus 2, still infinity, over infinity minus 1 is still infinity, so we're getting infinity over infinity. And this is indeterminate. So in this case, we don't know the answer. That's what it means when we say it's indeterminate. It means that we're not really sure. It's not saying that it diverges or converges or anything of that sort. It's just saying that we're not sure. So what we're going to now do is we're going to try one of our tricks we've looked at in order to see if we can get it to come to an answer that converges or diverges. So because this one has an n in the bottom, what I'm going to do is I'm going to divide everything by my n in this case, which is to the highest power. So this is going to be the limit as n approaches infinity, 5n over n plus 2 over n divided by 3n over n minus 1 over n. Now doing this n and n here, 5n and n, the n's will cancel. Same thing with the 3n over n. So this leaves us with the limit as n approaches infinity, 5 plus 2 over n over 3 minus 1 over n. Now applying our limit at this point, what do we get? Well, the 5 is a constant, so it's not affected by this. So then we take plus the limit of 2 over n. As n goes to infinity, this is going to be 2 over infinity. It's going to become increasingly small, become infinitesimal, basically going to 0. So this is going to go off to 0. This is also going to go off to 0, leaving us with 5/3. So in this case, this sequence actually converges to the point 5/3. Now for our second sequence, we have an is equal to 3n squared plus 4n minus 9 divided by n squared plus 2. Now this is going to be the same basic idea of what we just did, right? We're going to plug in our infinity, n squared, so infinity squared times 3 is still infinity, plus 4n, which is 4 times infinity, which is going to be infinity. So infinity plus infinity is infinity, minus 9, still infinity. We plug in infinity squared plus 2, still infinity. Again, this is going to be indeterminate, so we need to do something to change the form of this so we can take the limit. So when we take the limit as n approaches infinity, 3n squared plus 4n minus 9 divided by n squared plus 2. We are going to again divide by n squared in this case, the thing in the denominator that has the highest power, our variable that we're taking the limit for. So we're going to divide everything by n squared. That's why I left a space here. Divided by n squared, divided by n squared. And now these two n squares will cancel. These two will cancel, leave us with 1. One of these n's will cancel with this n, and we are left with the limit as n approaches infinity, 3 plus 4 over n minus 9 over n squared divided by 1 plus 2 over n squared. So now once we evaluate this limit, what's going to happen? Well, this term's going to go to 0. This term's going to go to 0. This term is going to go to 0, and we're going to be left with 3 over 1, or 3. So this sequence converges to 3. Our next sequence is going to be an is equal to 7x plus 3 divided by 3x minus 5. So if I take the limit as n approaches infinity, 7x plus 3 over 3x minus 5. Again, if I were to plug in my infinity, I'd get infinity over infinity, so it's indeterminate. So what I'm going to need to do is I need to do another trick. Well, in this case, same one. In this, I put in x's. I'm going to put n's. These should have been, that's fine. I can just change this to x. That's fine. As x goes to infinity. So in that case, what's this going to be? Well, this is going to be the limit as x approaches infinity, 7x over x plus 3 over x divided by 3x over x minus 5 over x. These x's will cancel. So now once we evaluate our limit, we have 7 plus 3 over x. This is going to go to 0. We have 3 minus 5 over x. This is also going to go to 0. And this will leave us with 7 thirds. So this converges to 7 thirds. For our next sequence, we have an is equal to the square root of 16x squared plus x minus 4x. So again, we're going to set this up as the limit as n approaches infinity, the square root of 16x squared plus x minus 4x. So as before, let's first try plugging in infinity. So I get infinity squared is infinity times 16, still infinity. Infinity plus infinity is infinity. Square root of infinity is infinity. 4 times infinity is also infinity. So we have infinity minus infinity, which means that it's indeterminate. So what we're going to do now is we're going to do a different trick this time to get it to a form we can use. But let's first look at why does our trick we already talked about, where we divide by the largest power in the denominator, not work? Well, in this case, we don't have a denominator. But one of the major mistakes I see students do when we talk about these tricks is they'll see that they have x, they'll just try dividing by it. So let's try it. So if we take the limit as n approaches infinity, square root of 16x squared plus x, we'll divide this by x, minus 4x over x. And we're going to focus on this term here. So because we have an x and we want to divide a square root term, what we're going to do is we're going to change this to a square root by using the fact that x is equal to the square root of x squared. So then rewriting this, we're going to have that this is equal to the limit as, I keep doing this, I do n, but I write x in the formula. I don't know why I keep doing this, but sorry about that. So we have the limit as x approaches infinity, square root of 16x squared plus x divided by the square root of x squared minus 4x over x. Now, whenever I have a square root like this, right, when you have the square root of a over the square root of b, you can rewrite this as the square root of a over b. So this then becomes the limit as x approaches infinity, square root of 16x squared plus x, and this is going to be divided by x squared. But what I'm going to do is I'm also going to use the trick that, or the rule that if I have something like a plus b over, I don't know, c, this is the same thing as saying a over c plus b over c. So I'm just going to do that now to make things a little faster. So this is going to be 16x squared over x squared plus x over x squared, all into the square root, minus 4x over x. So now let's do some cancellation. So we get 16 there. This x cancels with this x, and this cancels with this. This is going to leave us with the limit as x approaches infinity, square root of 16 plus 1 over x minus 4. Now, if we evaluate our limit, what happens here? Well, this 1 over x, just like before, goes to 0. Because it's 1 over infinity, it becomes infinitesimally small. So this goes to 0. This is going to give us the square root of 16 minus 4. So we get square root of 16 is 4, minus 4. And this will leave us with 0. So now let's look at the method that I was going to show you how to do, which is we're going to multiply by the reciprocal. So the reciprocal for something like this, the square root of 16x squared plus x minus 4x is going to be the square root of 16x plus x plus 4x. So we're going to multiply by the square root of 16x squared plus x plus 4x. But we can't just change what this formula is. So what we're going to do instead is we're going to multiply by the reciprocal over itself, because anything over itself is equal to 1. So this is going to be divided by 16x squared plus x plus 4x. So now when we do this, what's going to happen when we multiply out our terms? Well, we're going to have a square root of 16x squared plus x times 16x squared plus x under the square root. It's going to be this times this, the same term, so it's going to be a square of a square root. This is going to give us 16x squared plus x. Then we're going to do our outer terms, which is going to be plus 4x square root of 16x squared plus x. So then we're going to do our inner terms, which is going to be minus 4x square root of 16x squared plus x. And then we're going to do our last terms, minus 4x times 4x, which is going to give us minus 16x squared. And then this is all going to be divided by this bottom part of our reciprocal term. So we're going to get square root of 16x squared plus x plus 4x. Now, looking at these terms, you'll see in the middle here we have 4x times the square root of 16x squared plus x minus 4x times the square root of 16x squared plus x. So this is going to cancel with this. The 16x and the minus 16x squared, are also going to cancel. So this is going to leave us with the limit as x approaches infinity, x divided by the square root of 16x squared plus x plus 4x. Now, if we were to evaluate our limit here, we would still get infinity over infinity. It's still indeterminate. So now what we're going to do is we are going to use our trick where we're going to divide by the largest term in the denominator, which is x. So just like we did here, we're going to do the same idea to divide this term by x. So this is going to be equal to the limit as x approaches infinity. This is going to be x over x divided by, I'm just going to add the square root of x squared to begin with. So this is going to be square root of 16x squared plus x. It's divided by the square root of x squared, so I'm going to put that inside, and then I'm going to split it. So this is going to be divided by square root of x squared. This one's going to be divided by the square root of x squared, and then plus 4x over x. Okay, so now let's do some cancellation. X over x is going to give us 1. We're going to have 16. This is going to cancel with this, and this is going to cancel with this. And this is going to give us the limit as x approaches infinity, 1 over the square root of 16 plus 4, which is going to give us 4 plus 4 is equal to 1 over 8. So this is actually the term we're looking for. So while it appears this one does give us an answer, and you might think that this is the answer, remember that when we have something like this, we didn't have a power in the denominator, meaning that when we did this trick, it looked like everything was working out okay, but in the end, it really wasn't something we could do. So this approach actually is wrong. It should have been first we multiply by the reciprocal, then we divide by the largest power denominator, and we will get 1 over 8. For our last problem like this, we have the sequence an equals 2 over 5n squared. So again, we're going to set it up our limit. So this is going to be the limit as n goes to infinity, 2 over 5n squared. And as always, first thing we're going to do is we're going to try plugging in. So if we were to plug in infinity for n, we're going to get infinity squared as infinity. 5 times infinity is going to be infinity. So we're going to end up with 2 over infinity. So now we don't actually have an indeterminate form. We actually could just plug in and get this answer. So what's happening as my n in this sequence gets bigger and bigger and bigger? Well, if I were to plug in 1, right, let's look at what our sequence was. When we had 1, this was going to end up being 2 times 5 times 1, which is going to be 2/5. When we had 2, this is going to end up being 2 squared is 4. 4 times 5 is 20. This is going to be 2 over 20, or 1/10. When we had 3, this is going to be 3 squared is 9. 9 times 5 is 45. We're going to have 2 over 45. So what's happening with our sequence is that as our n gets bigger and bigger, the entire fraction is getting smaller and smaller and smaller, which means that this is going off to 0 as n goes to infinity. So it's converging at 0. So now what we're going to be doing is we're going to be looking at some limits to see if they exist and what the limit is when we evaluate it. So the first limit we have is we want to evaluate the limit as x goes to 3, so we're no longer going to infinity in this case, for x squared plus 4x minus 21 divided by x minus 3. Now you could actually do the same sort of tricks we did before, where you could try to divide by the largest power in the denominator and things like that. But actually in this case, because I have x minus 3 in the denominator, and I have some sort of square term up top, I'm assuming that this is going to actually have some cancellation. So let's see if we can actually break out this x squared plus 4x minus 21 and factor it and see if we have any cancellation. So we need to figure out what we can multiply that will give us negative 21 and add up to give us 4. So we're going to get that this is the limit as x approaches 3, and we're going to have, and because we have a negative on the end and a plus here, I'm going to assume that one of these is going to be plus and one of them is going to be minus. So what can we multiply? What two terms can we multiply to get negative 21? Well, in this case, it's going to be 7 and 3. So one of them has to be negative, one of them has to be positive. Well, because this 4 is positive, that would mean that the 7 needs to be positive, so that when we add them, they'll give us 4. When we multiply them, we'll get a negative 21. And of course, you can always distribute this and see if it works. So we get x squared, and then we do our outer terms, minus 3x, inner terms, plus 7x, last terms, minus 21. And of course, the minus 7, or the plus 7x minus 3x is going to give us 4. So that looks good. And now we're going to write our denominator in, x minus 3. And what we can do is we can cancel this with this. And now we're taking the limit as x approaches 3 on x plus 7. So we're going to plug 3 into this, and we're going to get that this is equal to 3 plus 7, or 10. Meaning the limit as x approaches 3 on this function, x squared plus 4x minus 21 divided by x minus 3 is equal to 10. Now let's do the limit. As h goes to 0, we have 5 plus h squared minus 25 divided by h. So if I were to plug this 0 in, what would I get? Well, 5 plus 0 is going to be 5. 5 squared is going to be 25. 25 minus 25 is going to be 0, divided by 0. So again, this is indeterminate. So I need to do something with this. Now, based on what I'm looking at here, I see that there's an h in the bottom, and there's some h's up top, but I can't really do anything with them in their current form. And so what I'm going to do is I'm actually just going to distribute this. So we have 5 plus h times 5 plus h, and let's see what we get. So this is then going to become the limit as h goes to 0. So we have our first term, 5 times 5, which is going to be 25, plus our outer term is going to be 5 times h, so that's going to be 5h. Our inner term is going to be h times 5, which is going to be 5h. And then our last term is going to be h times h, which is going to be h squared. So we have 25 plus 5h plus 5h plus h squared minus 25 divided by h. So I'm going to combine these two 5h's into 10h because they have the same power, h and h. This 25 is going to cancel with this negative 25. So this is going to give us the limit as h goes to 0, 10h plus h squared divided by h. Now, if you look, every term in our numerator has an h in it. So what I'm now going to do is I'm going to pull that out just to make canceling easier. You could cancel it here. It's perfectly fine. But I'm going to do it that way just to make it clear for everybody. So this is going to be the limit as h goes to 0 I'm going to pull an h out. So if I pull an h out of 10h, that's going to leave me with 10 plus. And if I pull an h out of h squared, I'm going to be left with h. And then this is divided by h. So this h will cancel with this h, and I'm left with the limit as h goes to 0, 10 plus h. So when I plug that 0 in, I'm going to be left with 10 plus 0, or 10. For our next limit that we want to evaluate, it's going to be the limit as x goes to infinity, and we have 4. I keep doing this. I keep switching x's and n's. I'm going to switch it to x's, even though on the paper it says n. So this is going to be 4x to the 5th power minus 3x cubed plus 2 divided by 2x to the 5th power plus 7x squared minus 1. As before, we are first going to try plugging in x and see what happens. So we're going to get infinity minus infinity. Well, already we can't do that operation. That's going to be indeterminate. And we have infinity plus infinity. So we're getting infinity minus infinity over infinity. So that really doesn't tell us anything that we can use. So what do we do in this case? Well, we've got a couple tricks up our sleeves we talked about. We looked at where we could try factoring things or changing the form of it to see if there's any cancellation. We looked at the fact that we could divide by whatever variable has the highest power in the denominator, or we could try multiplying by the reciprocal. Those are some of the tricks we've learned. Well, in this case, because I have x's to various powers in a fraction, I'm going to try dividing by x to the highest power, which is to the 5th power. So this is going to be the limit as x goes to infinity, 4x to the 5th power divided by x to the 5th power minus 3x cubed divided by x to the 5th power plus 2 over x to the 5th power divided by 2x to the 5th power divided by x to the 5th power plus 7x squared divided by x to the 5th power minus 1 divided by x to the 5th power. So this x to the 5th power is going to cancel with this x to the 5th power. This x to the 5th power is going to cancel with this one. This x cubed is going to cancel with 3 of the x to the 5th, which is going to leave us with x squared. And then this x squared is going to cancel with 2 of this x to the 5th, leaving us with x cubed. So what we have here is the limit as x goes to infinity, 4 minus 3 over x squared plus 2 over x to the 5th divided by 2 plus 7 over x cubed minus 1 over x to the 5th. And now, if we evaluate our limit, what's going to happen? Well, this 4 is a constant, so it's not going to be touched. Minus 3 over x squared. If I plug infinity over to that, that's going to be 3 over infinity, which means it's going to go to 0. Plus 2 over x to the 5th. Same thing, when I plug infinity, that's going to go to 0. This term's going to go to 0. This term's going to go to 0, and we're going to be left with 4 over 2, or 2. So the limit of 4x to the 5th minus 3x cubed plus 2 divided by 2x to the 5th plus 7x squared minus 1 is equal to 2. Our next limit is we're going to be looking at the limit as x approaches negative infinity, and we have x cubed plus x to the 5th. Now, we can actually kind of plug this in here, and what's going to happen? Well, because these are odd functions, right? If I plug in a negative into a cubed function, I'm going to get a negative back out. If I plug a negative into a function to the 5th power, I'm also going to get a negative back out. So if I were to just plug this in, I would get negative infinity plus negative infinity, which would be, of course, negative infinity, but that really kind of equates to negative infinity plus infinity. It's kind of a weird one. So what we're going to do is we're actually going to just change it a little bit, where what we're going to do is we're going to pull out the highest x power. So this is going to be the limit as x approaches negative infinity, and I'm going to pull x cubed out of this. So we have x cubed, and this is going to be 1 plus x squared. Now you might wonder, why did I do this? Well, now because what's going to happen is when I evaluate this, this is going to be equal to, I'm going to plug negative infinity into this, I'm going to get negative infinity. 1 plus, well now this is a square term. So negatives become positive. So this is going to be plus infinity. Well, in this case, infinity plus 1 is just infinity. So now I have infinity times negative infinity. Well, infinity times infinity, you can definitely do. It's just bigger infinity. And because I have a negative times a positive, this is going to give me negative infinity. Now, you might wonder, why does it work this way? Well, the intuitive sense is that if you look at our original terms, x cubed plus x to the fifth, they're both growing towards either positive infinity or negative infinity, but they're not growing at the same rate. So as I plug terms into x cubed, right, I plug in 1, I get 1. When I plug in 2, I get 8. When I plug in 3, I get 27. Well, when I plug into the fifth power, this is going to grow even faster, meaning that this is eventually, while they're both going to infinity, x to the fifth is going there faster, meaning that it's going to kind of dwarf anything that this term is doing. So really, it's just sort of saying x to the fifth is going to go off to negative infinity. For our next problem, we're going to be taking the limit as x approaches infinity, square root of x squared minus 81. So as always, if we were to first try plugging this in, what's going to happen with this? Well, if I evaluate this, if I plug infinity into x, it's going to give me infinity squared is infinity. Infinity minus anything that's not infinity is going to be still infinity. So this is just going to give me the square root of infinity, which is equal to infinity. So I didn't even have to do anything to clean this one up. I could just evaluate the limit of it, and I'm going to get that this is going to go to infinity, which kind of makes sense because we have this x squared minus 81. And anywhere that my x squared is big enough that's over 81, so basically it has to be, when x is greater than or equal to 9, because if I have a term that's less than that, I'm going to get a negative square root, and that's going to give me a complex number. But we're not worried about where is our domain for this function. We're worried about what happens with its behavior as it goes off to infinity. So as it's going off to infinity, what's happening? Well, this x squared is getting bigger and bigger and bigger and bigger, and it's going to continually get bigger forever. Well, the square root of something that's continually getting bigger, while the square root does slow it down, it's still going to go off to infinity. So the answer is infinity. We didn't have to do any sort of tricks to get this into a form that we could solve. It's just, in this case, evaluate the limit. On this problem, we have a graph that represents some function, and we're going to be looking to see if the given limits exist and what they're equal to. And if they don't exist, we'll just write D and E for does not exist. So the first one asks us for what is the limit as x approaches 2 from the left on our function. So looking at this graph, if you look at as we approach 2 from the left, we are approaching what value? Well, if you look at it's the bottom left line, means that we are at 25. And while it is not equal to f of 2, right, because that makes it's a discontinuity, meaning it makes a jump. In this case, we have that the limit as we approach from the left is going to be equal to 25. Now, the next problem is, what about if we're approaching from the right? Well, in this case, it's actually jumped up 1, so we're to the right of 2, meaning we're greater than 2. And as our limit gets closer and closer to 2 from the right side, we are approaching the value of 26, right? Because these are straight lines, so they're not really changing. We're at 26, but we're approaching a value that's at 26. The next question then says, what is the limit as x approaches 2? Now, in this case, we have to consider the fact that a limit only exists if the left-hand limit is equal to the right-hand limit. And we have the left-hand limit is 25. The right-hand limit is 26. And because 25 does not equal 26, this limit does not exist. So does not exist. The next question asks, what is f2? So f2 is going to be, what is the value at 2? So if I were to look at this function and see going to x equals 2 and going up to wherever that point is included, if you look, there's the two lines that stop at 2, but the filled in dot is the top one, meaning that f2 is going to be 26. Now, the last two parts of this are looking at the limit as x approaches 6 on our function, and then what is the value at 6 on our function. So we'll take the limit as x approaches 6. So looking at this, we have a line that looks like it's at 24. So as we approach from the left, it's equal to 24. As we approach from the right, it's equal to 24, meaning that the answer from the left and the right is 24, and the fact is that this limit exists because both of the limits from the left and the right agree with each other. The next thing asks us, though, what is the function at 6? And because it's on that line, it's also equal to 24. So because of this, because we have a left and right-hand limit that both give us the same value, that means the limit exists. And the fact that our limit, as x approaches some, let's call it a, our function at a is equal to the function at a, this means, sorry, this should be function x. This means that this is actually a continuous function at x equals 6 because the limit is a certain value at 6. It's equal to the value of the function at 6. So therefore, it's actually continuous around the point 6. For our next problem, we have a set of limits, and we want to try to draw the graph on our Cartesian plane to see what this graph might look like. Now, I am freehanding this, and I don't know the exact values of these functions, so it's not going to be exact, right? So just saying something goes off to negative infinity, for example, I don't know if it's curving off to infinity really quickly or slowly approaching, or if it's a straight line. All I know is that it's going in that direction. So our first limit says that our limit as x approaches -2 at f of x equals negative infinity. Now notice this is not a left or a right-hand limit, meaning that if I look at what the limit is as I approach -2, this is both from the left and from the right, meaning that I have what looks like a vertical asymptote right here, and as I approach this limit from the left, I'm going off to infinity. As I approach this limit from the right, I'm going off to positive infinity. Our second limit is we have the limit as we approach x equals 1, which is going to be right here. As we approach from the right, we're going to go off to negative infinity. So I'm going to, again, just kind of draw something like this for now. So as I approach from the right, I'm going to go off to negative infinity. So I don't know exactly what this looks like, but maybe something like this. Our third limit says that as we approach from the left, as we approach 1 from the left, we're approaching the value 2. So if I go to 1, 2, then this means that I'm approaching some value here. So what I'm going to do is I'm first going to actually do the next limits to see if there's anything that causes something to happen in between these. But we're approaching this value here. We'll get to that. Okay, no, it looks like we have our limit off to infinity and negative infinity. So I'm going to put maybe just that this kind of goes like that, right? So it's kind of hard to say exactly what it's doing because we don't know what the behavior is in between. We just know that as we approach x equals 1 from the left, we're approaching the value 2. And this may be inclusive, it may not be. We'd have to know what f of 1 is. For my function f of x, if I take the limit as x goes to infinity, this is going to approach the value 3. So it means we're going to be approaching this value here. So we could almost think about having a horizontal asymptote that we're going to approach, but never touch. And then the last limit is, on f of x, as we take the limit as x goes to negative infinity, it's going to approach -1. So this means that, again, it's going to be almost like we have a horizontal asymptote that we are approaching, but never touching. So this is what our function looks like. We have a line starting at -1 as we go off to negative infinity. As it comes up to -2 from the left, it's going to go off to infinity. Then we have the point as we approach -2 from the right, it's going off to infinity. So if we're kind of coming down, we're approaching as we approach x equals 1. From the left, we're approaching the point 2. As we're approaching from the right, we're going off to negative infinity. And as we take x going off to infinity, this is going to approach but never touch the value 3. So this is what our graph looks like. So if you kind of ignore my dotted lines, we have a line that goes like this, and then like this. For our next couple problems, we're going to be evaluating some more limits. So this one is we're going to be taking the limit as x approaches -3 from the right. This is going to be on the function x plus 2 divided by x plus 3. Now, if we were to try to plug in x equals -3, in the denominator we would get -3 plus 3 is going to give us 0 in the denominator. So we can't really do that. Now, in this one, there's not really any trick to solve this one. So what we're actually going to do is we're going to plug some values in to kind of see what the behavior is as we approach from the left. So whenever you're doing a right or left-hand limit, sometimes you're just trying to look at the behavior of, is it approaching a specific value? Is it getting bigger and bigger and going off to infinity? Is it getting smaller and smaller and going off to negative infinity? What's it doing? So in this case, we're going to have an x value, and then we're going to have the output of this when it's plugged into our function f of x. And because we're approaching -3 from the right side, this means we're going to have numbers that are bigger than -3. So I might do something like -2.9, -2.99, and -2.999. And we'll see if this kind of gives us an idea of what's happening. We're now going to plug in this -2.9 into x. We're going to get -2.9 plus 2 divided by -2.9 plus 3. So I'm going to plug that in my calculator, and I'm going to get, I got -9. And now I'm going to plug in -2.99, and I'm going to get -99. Now I'm going to plug in -2.999, and I get -999. So what's happening as we're getting closer and closer and closer to -3 from the right side? Well, as I get closer and closer and closer, it's getting bigger and bigger and bigger, but in the negative direction. Meaning that if I had to figure this out, I would say that this is going to negative infinity. So let's try to think intuitively why this might be. Well, because as I approach -3, this top term is going to -1, right? So it's getting closer and closer and closer to -1. But what's happening with this bottom term? Well, this bottom term is getting smaller and smaller and smaller, because when I had -2.9, it's -2.9 plus 3 is 0.1. -2.99 is giving me -0.01. This one is giving me -0.001. So while this term isn't really changing, it is changing a little bit because I am still approaching it, but it's approaching a specific number. This is getting smaller and smaller and smaller. So if my denominator is getting smaller and smaller and smaller, the entire fraction is getting bigger and bigger and bigger. But because this top term is negative, even though this bottom one is positive, this means that while the entire fraction is getting bigger and bigger and bigger and approaching infinity, it is a negative because of this term here, which is going to be something that's negative, right? So it's approaching -1. So it's approaching negative infinity. What about if I wanted to determine the limit as x approaches -5 from the left on x squared minus 5x divided by x squared minus 10x plus 25. So for this problem, first thing as always, we're going to try plugging in -5 to see if we can figure out what it might be, and look what happens as we approach from the left. So it'd be 5 squared, -5 squared is going to be 25. -5 times -5 is going to be 25. So 25 minus 25 is going to be 0. This is going to be 25 minus 50 plus 25. So 25 plus 25 is 50. 50 minus 55, we're going to get 0 over 0. It's indeterminate. So we're going to do the same thing we did in the last problem. We're going to have an x value, and we're going to have the output of our function. So because we're approaching -5 from the left, this means that we are going to have a number that is less than -5. So what I might do in this case, I might say, okay, well, I'm going to take -5.1, -5.01, -5.001. Basically, we're getting closer and closer to 5 from the left, because that means we're more negative than -5. And let's see what happens with this. So give me a second, and I'll write these down. Okay, so here's what we got as we plugged in values from the left to -5 as they got closer and closer and closer. So when I plugged in -5.1, I got 0.50495. When I plugged in -5.01, I got 0.5005. And when I plugged in -5.001, I got 0.500005. So what's happening in this case? Well, it looks like this is approaching 0.5. So now let's actually double check our work, right? I just wanted to show you that we could solve this numerically, just like you can pretty much any limit. But let's see what would happen if we tried to solve this analytically. So in this case, because we have x plus 2 over x plus 3, I'm going to do my trick where I divide by the x with the highest power, which in this case is just x. So this is going to end up being the limit as x approaches -3 from the right. This is going to be x over x plus 2 over x divided by x over x plus 3 over x. So the x over x's are going to become 1. So what we have is we have the limit as x approaches -3 from the right, 1 plus 2 over x divided by 1 plus 3 over x. So if we plug in our 3 into this case, or -3, sorry, this is going to be equal to 1 minus 2 over 3 divided by 1 plus minus, so I'm going to make this net minus 3 over 3. And what's going to happen? Well, of course, this is going to become -1, and we're still going to end up with a 0 in the denominator. So that one really didn't work to help us solve it analytically. This is why we actually solved it using a numeric method. Same idea with this one. If we decide to divide by x squared, we're going to end up with the limit as x approaches -5 from the left. We're going to have x squared divided by x squared minus 5x divided by x squared divided by x squared divided by x squared minus 10x divided by x squared plus 25 divided by x squared. So what's happening here? Well, this term's going to go to 1. This term's going to go to 1. This is going to go to 10 over x. This one is going to go to 5 over x. And if we plug in our 5 in here, we're going to get 1 plus 5 over -5 divided by 1 minus 10 over 5 plus 25. So actually, so this should be -5, so this should be plus. And this one becomes plus. Yes, we had 1 minus 5 over -5, which is going to give us 1 minus 1, or 1 plus 1. And this one is going to be 1 minus 10 over -5, so it's going to be plus 10 over 5, good. And then, of course, we're also dividing by our x squared, which in this case is going to be -5 squared, which is going to be 25. This is going to be equal to 1. So we're going to end up with 1 plus 2 plus 1 is 4. So this is going to be 2/4, which is equal to 0.5. So this one does agree with what we got. Now, is there a way that we could analytically solve this other one? Yeah, there is, but for now, I just mostly wanted to use these problems to show that if you have a limit that is approaching from the left or right, and you're approaching some point where you have that it's disjoint, meaning that you can't actually plug in the value, sometimes the approach you might take is you might plug in values as you get closer and closer and closer to determine what the behavior is and what you're approaching from that specific side. For our next limit, we're taking the limit as x approaches 6 from the left, and we have x squared minus 6x divided by x squared minus 12x plus 36. If we were to try to plug this in to evaluate what's going to happen, well, this is going to become 36 minus 6 times 6 is 36, get 0, divided by 36, plus 36 can be 72, minus 12 times 6 is 70, minus 72, so this can become 0 over 0. It's indeterminate. So what do we do now? Well, we could try seeing if there's anything we could cancel. So first thing I'm going to do is I'm going to actually try pulling out a 6 from the top. So this is going to be x approaches 6 from the left. I'm going to pull an x out. So this is going to become x times x minus 6. And for the bottom, I'm going to see, is there anything that I can factor? Is there anything that adds up to negative 12 and multiplies to give me positive 36? And the answer is, yeah, and it's going to, of course, match this. It's going to be x minus 6 times x minus 6. Of course, we can double check this, right? If I plug this in, first, x squared, outer, inner, minus 6, minus 12x, or minus 6x, minus 6x, 12, minus 12x. And then last, minus 6 times minus 6 is positive 36. Great. So now we're going to cancel one of these with one of these. And we're left with the limit as x approaches 6 from the left, x over x minus 6. We have x over 6, x minus 6. If I were to plug in my 6 now, what happens? Well, I end up getting 6 over 0. So I still have something that I can't plug in. But what I could do is I could consider what's happening as I'm approaching from the left. So if I had a value that was just a little bit smaller than 6. Actually, you know what? Let's make it a lot smaller than 6. Let's say we plug in 5. If I were to plug 5 in, what's going to happen with this? We're going to get 5 over 5 minus 6. We're going to get negative 5. So if I plug in 5, I get out negative 5. If I were to plug in 5.5, I get 5.5 divided by 5.5 minus 6, or 0.5. So that becomes 5.5 divided by 0.5 is 11. As I plug in, let's say 5.9. X is 5.9. I get 5.9 minus 6 is going to give me minus 0.1. So I get 5.9 divided by negative 0.1. Sorry. This is going to give us 59. So what's happening is, as my x gets closer and closer and closer to 6 from the left, this bottom term is going to be getting smaller and smaller and smaller. So this term here is getting smaller and smaller and smaller. And because I'm to the left of 6, whenever I take x minus 6, I will always have a negative number, which means that if my denominator is getting smaller and smaller and smaller, my entire fraction is getting bigger and bigger and bigger, but in the negative direction. So that means that this is going to approach negative infinity as I get closer and closer to 6 from the left side. Our next limit we're going to be looking at is we're going to take the limit as x approaches 4 square root of 3x squared minus 2 divided by 2x minus 5. Now this problem, we actually have slightly different instructions on it. So I wrote that I wanted you to evaluate the limit using the appropriate limit laws, and if the answer does not exist, write D and E. So in this case, these are going to be much more straightforward limits. They're likely going to exist, but what I want to see is I want to see the steps taken to actually get it to the form where you're actually evaluating the limit. So before, what we've always been doing recently is we've been kind of just saying, okay, I evaluate the limit. But now let's actually break it down by our limit laws. So in this case, we're going to use our first limit law, which is the fact that if I have the limit of the square root of something, this is the same thing as taking the limit of whatever's inside, so 3x squared minus 2 over 2x minus 5, and then taking the square root of the entire thing, right? I can take that limit and I can move it inside. So now let's focus inside the square root. I have the limit of a fraction. So I'm going to take the limit of the numerator divided by the limit of the denominator. So this is going to be the limit as x approaches 4, 3x squared minus 2, divided by the limit as x approaches 4, 2x minus 5. And of course, I still have this all under the square root. Now, in the numerator of my fraction, I have the limit of two things added or subtracted together. So same thing with the denominator. So this is what I can use. This limit law is that the limit of some function f of x plus or minus some function g of x is the limit of f of x plus or minus the limit of g of x. So this is going to become the limit as x approaches 4, 3x squared, minus the limit as x approaches 4, 2, divided by the limit as x approaches 4, 2x, minus the limit as x approaches 4, 5. And of course, we have the square root of the entire thing. One last rule, and that is because all of our functions are not in terms of just a constant or an x term, what we're going to do is we are going to pull out our constants. I'm just going to draw this so I don't have to rewrite the entire thing again. So we're going to pull this 3 out, we're going to pull this 2 out. And technically, there is one more limit law that we're using, which is this one here. We're going to end up with 3 times the limit as x approaches 4, x squared, which that's actually using the limit law that if I have the limit of some function to a power, it's the same thing as taking the limit of x and then squaring that. So what does that mean? So it means this. If I had the limit of x approaches something, x squared, this is the same thing as taking the limit of x squared. So technically, we're doing a couple other limit laws, but I think this is a good enough form to kind of say we can evaluate it. So now let's evaluate this limit. So the first limit, we have 3 times the limit as x approaches 4, x squared. So we're going to plug 4 in, and we're going to get 4 squared is 16. 16 times 3 is equal to 48. Minus the limit of a constant is just a constant, so minus 2, divided by 2 times the limit as x approaches 4, x. So this is going to be 4 times 2 is going to be 8, minus limit of constant is a constant. And then this is under the square root. So we have 48 minus 2, which is going to be square root of 46. And then 8 minus 5 is 3. So we have the square root of 46 over 3. And this is using our limit laws to show how we got to this. And of course, if we wanted this as a decimal or something like that, this would be square root of 46 divided by 3, which is going to be equal to about 3.91, I'll just say 6. For our next problem, we're going to be doing the same thing. We're going to be using all of our limit laws to show what this limit is. So we have the limit as x approaches 3, x squared plus 2x minus 15 divided by x minus 3. And as I said before, you could probably just evaluate this pretty easily, or in this case, we might have to use a trick because we're going to get 3 minus 3 in the denominator. But let's find out what happens. So before we do anything, let's actually do that trick. Let's actually solve it first that way. So we're going to do our limit as x approaches 3, x squared divided by x plus 2x divided by x minus 15 divided by x over x minus 3 over x. This is going to cancel and give me 1. This is going to cancel one of these x's. This is going to cancel and leave me with that 2. Now, normally what we would do if we were solving this problem is we would just now plug it in, which we'd still run into an issue because we have the 1 minus 1. So what do we do in this case? Well, we would actually have to look at possibly what is the limit from the left and from the right. But it depends, because remember, that only really works if it's indeterminate. So what would happen at the top? Well, we'd plug in 3 plus 2 is 5 minus 15. So we would get something over 0, which means that our limit is either approaching infinity or negative infinity or does not exist, right? So what we're going to do, though, is let's do our limit laws to get it into that form that we talked about. So in this case, we have the limit of a fraction. So this is going to be the limit as x approaches 3, x plus 2 minus 15, which actually I'm going to combine those together. So that's going to be x minus 13 divided by 1 plus minus 3 over x. And then I'm going to take the limit of the numerator divided by the limit of the denominator. So this is going to be the limit as x approaches 3, oh, sorry, that was actually what I meant to do in that first step. It was supposed to be the limit of the top over the limit of the bottom. So what I meant is for this step, I'm now going to split it. So it's going to be the limit of x minus the limit as x approaches 3, 13, divided by the limit as x approaches 3, 1, minus the limit as x approaches 3 over x, which really I can pull that 3 out. So this is the same thing as saying 3 times the limit of 1 over x, which is x to the negative 1 power, which would be taking the limit of x, taking the whole thing to the negative 1 power. So when we evaluate this now, this term, of course, goes to 3. This is a constant, so it doesn't change. So we get 3 minus 13. This one is constant, so it doesn't change. This one becomes 3 over 3, which is 1, so we get 1 minus 1. So we still get that 0 in the denominator. We've just shown the limit rules of how we got there. For our next problem, we're doing the same sort of thing. This one, we're taking the limit as h goes to 0. 6 plus h squared minus 36 divided by h. Now, of course, if I plugged in, whenever I evaluate, I'm going to get a 0 in the denominator. So we know from our prior example that where we did one like this, we're first going to have to factor out the 6 plus h squared into its different terms. We're going to do some cancellation, get rid of the h in the denominator, and then we'll use our limit laws to evaluate. So while we're doing all this algebra to do elimination, we're not actually evaluating our limits. We're just going to leave that limit there for now. So what I'm going to do is I'm going to leave that limit there. So as this goes to 0, I'm going to do first, outer, inner, last. So this is going to be 36 plus 12h plus h squared minus 36 divided by h. The 36's are going to cancel. This is going to leave me with 12h plus h squared over h. I'm going to pull an h out. So this is going to be the limit as h goes to 0. H times 12 plus h divided by h. The h's will cancel. And now I am left with the limit as h goes to 0, 12 plus h. So now, of course, the only limit law I have to use is my limit of f of x plus or minus g of x is the limit of f of x plus or minus the limit of g of x. So this is just going to be the limit as h goes to 0, 12, plus the limit as h goes to 0, h. The limit of a constant is that constant. So this is going to be equal to 12, plus the limit as h goes to 0 on h is going to be 0. So I'm going to be left with 12. Okay, so now our next problem is that we have the limit as x approaches -6 on the square root of x squared plus 64 minus 10 divided by x plus 6. So as before, we're going to try using some of our tricks, because if I plug in -6 here, I'm going to have a 0 in the denominator. So which trick do I use? Because honestly, this looks a little bit like both. I've got a square root plus or minus something, so reciprocal. But also I do have a fraction, so there's already something down there where I could try dividing by whatever my variable is to the highest power, which in this case would be x. So I think let's try both. So in this case, what if we were to divide everything by x? So we would have the limit as x approaches -6, and then we have the square root of x squared plus 64. Now, if I divide this square root by x, we talked about this previously. This is the same thing as dividing by the square root of x squared. And then I can put that inside the radical, and then I can split it. So this is going to be x squared and over x squared, all under the square root, minus 10 divided by x over x plus 6 over x. So now we do some cancellation. This term goes to 1, this term goes to 1, and everything else seems fine. So now we have that this is equal to the limit as x approaches -6, square root of 1 plus 64 minus 10 over x divided by 1 plus 6 over x. Now, if we were to plug in -6 now, what's going to happen? Well, this is divided by x squared. If we were to divide by -6 now, this would be -6 squared, which is going to be 36. This would be divided by 2. We're going to get, it'd be divided by 36. So in this case, what really matters is this term here. If we plug in -6, we're going to get 6 over -6, which is -1. 1 minus 1, we're still getting a 0 in the denominator. So what we're going to do now is we're going to try multiplying by the reciprocal. So we're going to ignore this phase. Let's try doing the reciprocal. So going here, this is going to be equal to the limit as x approaches -6, square root of x squared plus 64 minus 10 divided by x plus 6 times, and remember the reciprocal is going to be this, but we're going to have a plus between the square root and the 10. So this is going to be the square root of x squared plus 64 plus 10 divided by the square root of x squared plus 64 plus 10. And what we're going to do now is we are going to multiply these terms out, and this is going to give us the limit as x approaches -6. So we have the square root of x squared plus 64 times the square root of x squared plus 64 is just going to be x squared plus 64. We're then going to do our outer and our inner terms. So we're going to get plus 10 square root of x squared plus 64 minus 10 square root of x squared plus 64. And then we'll do our last, which is minus 10 times 10, which is going to be minus 100. So these middle two terms are going to cancel. At the bottom, I'm just going to leave it the way it is. So there's going to be x plus 6 divided by, or times the square root of x squared plus 64 plus 10. Okay, so what I'm left with at the top is we have plus 64 and we have minus 100. This is going to give us minus 36. So this is going to be the limit as x approaches -6, x squared minus 36 divided by this stuff. I'm just going to write this as a squiggle. We'll come back to it when we actually are going to evaluate. Why am I doing this? Well, because let's look at this x squared minus 36. This can actually be split into x plus 6, x minus 6. So this is going to be the limit as x approaches -6, x plus 6, x minus 6 divided by x plus 6 square root of x squared plus 64 plus 10. So these x plus 6's are going to cancel. And now I could actually evaluate my limit. So we would go through all the same rules. We have a fraction, so we take the limit of the top over the limit of the bottom. We would take the limit of the first term plus or minus the limit of the second term. I'm going to assume we did all that. I'm kind of running out of space here. So what I'm going to now do is I'm just going to plug this in. I get -6 minus 6. This is, the top is going to be equal to -12. And then I'm going to plug in -6 here. -6 is going to be 36. 36 plus 64 is going to give me 100. The square root of 100 is going to be 10. So we get 10 plus 10. So this is going to be -12 over 20. So now we've evaluated, we have our answer. Of course, if we wanted to, we could plug this into a calculator and get the decimal value, or we could take the fact that it's -6 over 10, which means that it's -0.6. So there you go. That's how you solve this one. I know it's a little bit more complex. I just wanted to show you why sometimes you just have to try a certain trick and it's just not going to work. They're not always going to work, which is why we looked at different methods sometimes, like graphing functions and trying to determine what they approach, whether they converge on something, plugging values in, using numerical methods, things like that, right? These tricks are just that. They're tricks to try to get into a form that we can actually solve. For our next problem, we have 3x minus 2 is less than or equal to some function f of x is less than or equal to x squared minus 2x plus 1 for x values that are greater than or equal to 0. And we want to find the limit as x approaches 4 on our function f of x. So if we know that our f of x is always greater than or equal to this function and always less than or equal to this function, what we can do is we can look at what is the limit of this function as x approaches 4 and what is the limit of this function as x approaches 4, and see if it gives us some boundary conditions specifically to squeeze our middle function into a specific value. And this is, by the way, using Squeeze Theorem. So this is going to be the limit as x approaches 4, 3x minus 2 is less than or equal to the limit as x approaches 4, f of x is less than or equal to the limit as x approaches 4, x squared minus 2x plus 1. So now if we were to plug in 4 into each of these, this one would become 3 times 4 is 12, minus 2 is 10. So we have 10 is less than or equal to the limit as x approaches 4, f of x, and is less than or equal to, if we plug in 4 here, we get 4 squared is 16, minus 2 times 4 is 8, so 16 minus 8 is 8, plus 1 is going to give us 9. So it looks like this is not actually correct, right? Because if I plugged in, so 16 minus 8 would be 8, plus 1 is that. 4 plus that's 12 minus 2. Yeah, so this actually doesn't make any sense. The idea was this was probably supposed to be, this is probably a typo, this is probably supposed to be 2, in which case this would have come to 10 or something like that. In which case, what we're trying to say with the squeeze theorem is that if the value that, if this function f of x is always greater than this function, greater than or equal to, and this has a limit of 10 at x equals 4, and it's always less than or equal to this function, and that has a limit of 10 as x goes to 4, then this also would have to be equal to 4. So I think that was just a typo on my part. I think that was supposed to be plus 2 there, or this was supposed to just be minus x or something like that, where I was supposed to, you know, get some boundary conditions. The next problem says if f and g are continuous functions and f of 5 equals 4, so we have f of 5 equals 4, and we have the limit as x approaches 5 for 3 f of x minus g of x equals 10, then we want to find out what is g at 5. So what we're doing here is basically we're just doing some substitution, because we know if we have a continuous function at a particular limit, then the addition or subtraction of those limits at that point would also be continuous, which means that the point exists, which means we can then plug it in. So what we're going to do is we're going to take our f of 5, right? This is the function f of x at 5, at x equals, as x approaches 5, so at 5, we're going to plug that in to here. So this is then going to become, we have the limit as we, if we plug in 5 here, this becomes, actually, I'll just write it out. So the limit as we apply it, this will be 3 times f of 5 minus the limit as we plug in 5, this will be g of 5, and we have equals to 10. So we plug in our f of 5, this is going to be 3 times 4 minus g at 5 is equal to 10. 3 times 4 is 12, so we're going to subtract that. So we have 10 minus 12, so this is going to be minus g of 5 is equal to minus 2, which means that g at 0.5 is equal to 2. Not 0.5, the 0.5. Okay, so the next problem says, use the definition of continuity and the properties of limits to show that the function is continuous at a given number a for f of x equals, so we have f of x is equal to x plus 2x squared to the 4th power, and a equals -2. So to show that something is continuous, we would have to show that the left limit exists, the right limit exists, they're equal to each other, and they're equal to the function at that point. So what we're going to do is we're going to take first this function here, and I'm actually just going to take the limit, because if it exists to the left and right. So I'm going to take the limit as x approaches -2 on x plus 2x squared to the 4th power. So if I were to then evaluate this limit, this is going to become -2 plus 2 times -2 squared, and then this is all to the 4th power. So we get -2, so -2 squared is 4, 4 times 2 is 8, 8 minus 2 is going to be 6. So this is going to be 6 to the 4th power, which not sure what that is off the top of my head, so I'm just going to plug that in. 6 to the 4th power, I got 1,296. So 1,296. Now we need to evaluate whether that whether that function is equal at this point, -2. So of course, if we did that, we would get f of, what was our a is number -2. This would be, same idea, it would be -2 plus 2 times -2 squared to the 4th, which if you look at it is going to be exactly the same thing, 1,296. So this means that our limit as x approaches -2 on our function f of x is equal to the function at -2. So therefore, this function is continuous. For our next function, we have f of x is equal to x cubed if x is greater than or equal to 2, and 2x plus 1 if x is less than 2. So we have a piecewise function, and we want to look at our left-hand limit and our right-hand limit and determine what the limit is or explain why it's discontinuous. So what we're going to do is, and by the way, sorry, for this one we have a is equal to 2. That's our point that we're doing our limit at. So we're going to take our left-hand limit. So we're going to take the limit as x approaches 2 from the left, and we're going to take our right-hand limit. So we're going to have x approaches 2 from the right. And then if we are approaching from the left, which means we are less than 2, our function is going to be 2x plus 1. If we are approaching from the right, our function is going to be x cubed. So of course, using your limit laws, you would take the limit of 2x plus the limit of 1, but we're just going to evaluate by plugging in 2. So we get 2 times 2 is 4. 4 plus 1 is 5. If we look at our right-hand limit, we plug in 2. We get 2 times 2 is 4, times 2 is 8. So this means that because the limit as x approaches 2 from the left on our function f of x is not equal to the limit as our x approaches 2 from the right on our function, this means that it is discontinuous. It means that whatever's happening as we approach these values, as we get to 2 from the left, what's going to happen then is we're going to get up to 2. We're going to have a circle there to represent that it's not inclusive, and it's going to be a jump discontinuity where it's going to jump from 5 suddenly up to 8. The next problem is we have the function f of x is equal to x squared minus c if x is greater than or equal to 2, and c minus 2x if x is less than 2. Now for this one, this is a little bit different because unlike this one where we were checking, is it continuous? We're now saying what c would make it continuous. So we're going to do the same idea. We're going to take our limit from the left. So in this case, we're approaching the value 2. So we're going to take the limit as x approaches 2 from the left, and our limit as x approaches 2 from the right. And what we're going to do is we're going to set these equal to each other, so that way we have to see what c would make this true. So when we're taking our left-hand limit, that is x is less than 2, this function is c minus 2x. When we're taking a right-hand limit, it is x squared minus c. So if we were then to evaluate this limit, c is a constant, so we're not changing that. We're going to plug in 2 into this. We're going to get that this is equal to c minus 2 times 2, or 4. This one is going to be 2 squared, which is 4, minus c. So then what we're going to do is we're going to set our left-hand limit, right, equal to our right-hand limit. So we're going to say c minus 4 equals 4 minus c. So then what I'm going to do is I'm going to get my c to one side. So I'm going to add c to both sides. So plus c, and I'm going to subtract 4 from, or add 4 to both sides. So plus 4, and this is going to leave me with 2c is equal to 8. Divide by 2, and I'm going to get c is equal to 4. This is the value for c that would make these two have the same limit from the left and the right at the value 2. And now for our last problem, we're going to use our intermediate value theorem to show that there is a solution for the given equation on a specific interval. So our interval in this case is going to be from 1 to 2. And if you remember, our intermediate value theorem says that if we have some boundary a and b, then we have some associated f of a and f of b where they cannot be equal to each other. And that means that to get from f of a to f of b, as I travel from a to b, I would have to cross every value between them, right? The intermediate values. So we're going to look at the boundary conditions on our function x squared plus x minus 6, and we're going to see, does 0 exist in there? So we have x squared plus x minus 6 equals 0. So we're going to start by looking at our left-hand boundary. So we're going to have f of 1 is equal to 1 squared plus 1 minus 6, and this is going to equal 1 plus 1, that's 2, minus 6 is going to be negative 4. And then we're going to check our right-hand boundary. So we have f of 2. Now what we're going to do is we're going to plug a 2 in for each of these. We're going to get 2 squared plus 2 minus 6. So this is going to be 2 squared is 4, plus 2 is equal to 6, minus 6 is equal to 0. So this means that it's not exactly what we want with the intermediate value theorem. What we wanted actually is I should have made this something like -5 so that this would be above 0, but it is within the boundary. So in that case, does it exist in our boundary? Well, because we're not counting those boundary points, not really, but let's say, for example, we change the problem just a little bit, because I want to show you how the intermediate value theorem would work to show it. Let's say that this was -5, right? So we do -5, -5. Then whenever we did our first function, f1, we would get 1 plus 1 minus 5, which would give us -3. So this would be -3. If we plugged in our 2, this would be 4 plus 2 is 6, minus 1 would give us 1. So now in this case, what this would be saying, +1. What this would be saying is that to go from a value that is somewhere at -3, right? So we had 1, 2, so that means that it was like 1, we had a value here, up to +1 at 2, means that we would have to cross every value between here at least once. So for example, our function could be this, in which case 0 is included, or our function could be something like this, in which case we would have multiple zeros, but we would have shown at least that there was 1 0 that did exist. So this is all of our review for this upcoming exam. It's covering anything and everything on limits. I know some of the problems didn't work out exactly the way I'd planned to, probably because of typos or because I was making the questions very quickly for the review. But I do hope that this was helpful because you can kind of see all the things we're looking for and all the tricks we've learned and how to apply them to solve for your limits. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.